everybody. Welcome to the last talk of the day. I'm super excited to introduce Andre. So Andre Wibisono is a professor of computer science at Yale University. He's done a lot of very interesting work in optimization and different insights between discrete and continuous time dynamics. And today he'll be talking us about alternating mirror descent for constrained min-max schemes. Thank you, Andre. The floor is yours.
Thanks, Georgios. Hi, everyone. Thanks for having me here. It's good to be back in Berkeley and see everyone. So this is, I will talk about alternating mirror descent for constrained min-max games. And this is part of an ongoing conversation with Georgios here and also with Molly Tao at Georgia Tech. So today in this talk, we'll talk about the very simple case of a zero-sum bilinear game, possibly with constrained domain. So here P and Q are closed convex sets, and we have some arbitrary payoff matrix A. And they can be in different dimensions. So for example, if they're unconstrained, then the domains are Euclidean space. Or a very interesting example is when the constraints are the simplex, right? For example, like in all the games we have been talking about so far. Okay, and in this simple case, in this simple game, there is a well-defined concept of equilibrium, the classical notion of Nash equilibrium, right? Which is stable under unilateral perturbation. And we know that it exists if the domain is compact at least. And one way to measure the distance to the equilibrium is via this notion of duality gap, which is for any point PQ, for any strategy that you have, you measure this difference. And this is nice because you can show this is always non-negative and it is zero exactly at the equilibrium. So this can be one notion of how to measure distance. And today we'll talk about also about the regrets of the algorithms. So suppose the two players follow some algorithms or some dynamics. Then as usual in online learning, we can measure the regret of each player by following their action compared to the best static strategy in hindsight, right? And we can also do that for the second player. And typically, if you define them properly, then when you sum them up, the total regret of the players average over time will be related to the duality gap of the average iterates. Right? And here we are in the very simple bilinear case, so averaging still makes sense. And therefore, if we have an algorithm with no regret, meaning the regret RT grows smaller than T, then this average goes to zero, and we know that we have a convergence of the average iterates to the equilibrium. Okay. Okay, so we will study some different algorithms and understand what different properties they have. And a lot of this will be classical, and I know that this is the last talk of the day, so hopefully I can illustrate just some of the basic concepts and the simple story. And the theme of this talk will be the difference between continuous time dynamics and discrete time algorithms. And this is also something that we have seen over and over in some of the previous talks, that typically at a very general dynamical systems level, given a continuous time dynamics, usually described as a differential equation with some vector field V, there are many different ways we can discretize that and implement them as algorithms. The most basic way is what's called the forward method, or what's called the Euler method. Here we are approximating the velocity just by the finite difference with some step size eta, and we are putting the vector field at the previous point. So this is like a Markov chain, that if you know where you are at xk, then you can compute where you want to go next. But where you go next will be deviating from your continuous time curve, right? Because in the continuous time flow, you are actually always following your velocity, and here you are doing some discrete step approximation with step size eta. On the other hand, the other version, the backward version, is the following, where you approximate the vector field by the point of your next iteration. Right? So this is an implicit update. If you know where you are at xk, you need to solve this update. So this is an implicit update. And there are many ways to solve this depending on what your vector field is. And you can say that if your vector field has some smoothness property, then this is always well defined when the step size is not too large at least. And the backward method is what's called the adjoint of the forward method. Formally, that means that the backward method, the way you get this would be, you can run the forward method with a negative sign here and then invert that. right? Because if you look at this update, to get xk plus 1, you can bring this whole expression to the left, right? And then say that so xk will look like you run the forward method from xk plus 1 with a negative step size, right? So you need to invert that. Okay, so in general, the forward and backward method are the two basic first order methods, and they have these opposite properties. Forward method is always explicit, but typically it's less stable. The backward method is implicit. It requires more computation. It requires some computation in each iteration, but you can show very nice properties of this, right? And we'll explore some of this today. So for example, to start off with a very basic setting, let's look at what happens in the unconstrained setting when the domains are Euclidean spaces. Let me call the points x and y for now, so that it's more clear that they are in the Euclidean space. Here, the equilibrium is at 0, 0. At least that's the point of interest. And one basic method is what's called the simultaneous gradient descent ascent, where it looks like the x player, the first player, wants to minimize this objective function, which is linear in x. And what they do is just run gradient descent. And this is the gradient of your objective function with respect to x, right? And with some steps as eta. And similarly, the y player also runs gradient ascent because they want to maximize this objective function. So this is the gradient with respect to y, but there is a plus sign because they want to maximize. And the point to note here is that they do this simultaneously, right? So this means that if right now they're at this point xk, yk, they look at each other and then they make the move, and then they move to this point xk plus 1, yk plus 1. And as probably now classical, this doesn't have good properties because turns out this diverges. And you can sort of see why if you look at these circles as the contour set of the quadratic function. This is in the xy space. What happens is that at every iteration, if you are here, this update will bring you to a new point that's orthogonal to the contour set where you are now. So you always go out and you always increase your objective function. And algebraically, you can check that in each iteration, if z is the vector x, y, your radius always grows by at least 1 plus something, right? That scales with step size squared, but still bigger than 1. So the iterates themselves diverge to infinity, and yet when you average, you can show that this still gives the classical regret bound of square root t for the forward method. Right? Okay, so this is for the gradient ascent. If you take the step size to 0, you get continuous time gradient flow where x minimizes x transpose ay and y wants to maximize x transpose ay. Here, instead of diverging, they cycle, right? Because at each time we are really following the velocity, which is always orthogonal to the circle, to the contour line. So you always stay within the circle. And you can check that by checking that the time derivative of your radius squared is 0. So you always stay there. And this gives the ideal case of constant regret bound. Right? And so when you average over t, you get very nice convergence. And okay, so this is in continuous time. What happens if we do the backward version? So now they do simultaneous, but they do the implicit version, right? So here, xk and yk need to coordinate and plot simultaneously how to go to xk plus 1, yk plus 1, satisfying this condition. Right? This is, in this linear case, it's easy to see how to solve, right? Because you can bring this here and then you can invert the equation. But in general, this may require some computation. And here, the behavior is the opposite. Instead of diverging, instead of cycling, it actually converges because, in some sense, because of the opposite reason of the forward method, right? Because the backward method is what you get if you run the forward method with negative step size, basically. So here, if you start here, then you want to find a point such that if you were to take the opposite velocity, you would have ended up where you are. So you always go inside, and you can check your radius is decreasing in each iteration. And this also gives a constant regret, right? And there are techniques like optimistic and extra gradient and so on that are trying to approximate this proximal method. That's one interpretation. Okay, so we've done forward, we've done continuous, we've done backward. Now, what about alternating? So here the updates look different. So X plays the forward method. So X makes a move based on where the Y player is right now. So X moves, but the Y player looks at the new value of X before they make the move. So they do the update one at a time, right? Or equivalently, the X plays the forward version, Y plays the backward version. Right? So alternating is also forward backward for this particular splitting. And here, the behavior really recovers the continuous time behavior. And this is part of result of a beautiful paper by Bailey, Giddel, and Yerkes a few years ago that says that in this quadratic case, the energy itself is not conserved, the radius squared is not conserved, but there is a modified energy where you take the original sum of squares, but then minus a small correction term that depends on step size. Right? And in this case, you can check that this modified energy is preserved in each iteration. And graphically, you do the update, you make 2 updates within each iteration, and you can see that, or at least you can show that it's actually conserved. So they have very different behavior. And so here's another example for the quadratic function for the alternating gradient descent ascent. When the step size is small, these are the iterates of the algorithm. And here we are plotting the actual energy, the actual sum of squares, which are oscillating, versus the modified energy, which is exactly constant. When the step size is small, the trajectory still looks like a circle. But if you increase the step size, they look more like an ellipse, right? Because the correction becomes bigger. Here, the energy becomes more unstable, or like becomes more wild, but the modified energy is still constant. So unconstrained Euclidean case, we know things very well. And the question in this talk is what happens if we are in the constraint setting, if we don't use gradient descent, but we use mirror descent? Do we still get the same kind of behaviors? So here's a summary of what happens in this unconstrained setting. Continuous time, cycles, conserves energy. I don't talk about volume conservation and so on, but you can say that in continuous time, this conserves volume. In discrete time, there are these 3 different behaviors. The forward method always increases energy, it diverges. The backward method decreases energy, it converges. And the alternating method conserves a different kind of energy, a modified energy in the quadratic setting. Okay. Okay, so this is in the unconstrained setting. Now I'm going to describe what happens in the constrained setting using mirror descent. But before I do that, are there any questions so far? Yes, I mean.
Sorry, why do you configure mirror? Just project.
Why? You can do projected gradient descent. Mirror descent is very nice. It will be much nicer if we work with dual space. Yes, I'll show you. Yeah, but in principle, we can run any algorithm. Yeah. Okay, thank you. So first, let me give a really brief review of mirror descent for optimization, because part of what I'm hoping to illustrate today is the difference between the behavior for optimization and for games. Because for optimization, at this point, we have a pretty well studied understanding of the behavior of basic first order dynamics and the various discretization. What happens if you run the forward method, the backward method, alternating, and so on. But for games, you have much more variety in the behavior. Okay, so for mirror descent, where it comes from originally is for constrained optimization. So suppose you want to minimize some objective function f, still in a domain P. The mirror descent algorithm looks at the following. At each iteration, you're at pk, and you want to minimize this regularized problem, where the first term is the linear approximation to your objective function, and then you regularize by what's called the Bregman divergence. So here there's a step size eta as before. Phi is some convex regularizer. We assume phi is steep and the gradient goes to infinity and so on. And the Bregman divergence measures the distance between the function and the linear approximation, right? So when this phi is convex, it's always non-negative, and we use that as a distance from the 2 points. So for example, in the unconstrained setting with quadratic regularizer, the Bregman divergence is just the L2 distance square. And then this mirror descent gives back the classical gradient descent. But on the simplex, if we choose the regularizer to be negative entropy, then the Bregman divergence becomes KL divergence. And then this gives us the multiplicative weight update algorithm. Right? But in general, you can pick any regularizer you want. Okay, now if you write down the optimality condition of this problem, then the new point pk plus 1 has to satisfy this equation, where the gradient of phi applied to the new point has to be equal to the gradient of phi of the previous point minus this gradient that you want to add. So previously, gradient descent would be without this gradient phi, would be identity. But now here we do the gradient update in the dual space, meaning in these variables. So more precisely, if we let's just define this variable to be xk. And really, if you define it this way, then you can say that pk is also the gradient of a dual function, right? That's the inverse. And so this pk you can write down as this gradient. So this mirror descent corresponds to the following algorithm in a dual space, where x is your new variable now. And at each iteration, you perform an update by this vector field. Right? But this vector field is not the gradient of some function with respect to x, right? It's we will see that it's what's called the natural gradient descent for that. So you may have seen this this figure to illustrate mirror descent usually, where we are in some constrained domain. So from pk, we first map to dual space. We do the gradient update here, and then we invert this back to get our new point. And this inversion may require projection or you stay in the domain. And what happens here is that in the original problem, you are trying to minimize some function f. When you push it to the dual space, your new function of interest is this just a push forward function. Right? And working with Bregman divergence in the primal space really corresponds to using the Hessian metric defined by phi. When you push it by this what's called the mirror map, in the dual space, your metric is given by the Hessian of the dual function. Right? So there is this very nice correspondence. And this becomes even more interesting in the continuous time. So if you take this eta goes to 0, eta is step size, right? In the dual space, you recover what's called mirror flow. And this is in the x variable, right? But if you translate this in the primal variable p, if you just plug in p to be this this value, then this gives what's called the natural gradient flow for p. So this is the gradient flow for minimizing this objective function f, but using this Hessian metric. So when you have a metric, you should multiply the gradient by the inverse metric. And both of these flows are descent flows, meaning that your objective function of interest is always decreasing, right? So you never increase. And you can show convergence guarantees if you assume something more. So for example, if you assume that your objective function satisfies some strong convexity condition relative to this function phi, then you can show that this ODE minimizes your objective function exponentially fast in continuous time. Yes.
What is the condition that we know in order to have the Hessian to be empirical?
This is impossible if when phi is strictly convex, right?
Okay.
Yeah.
Oh, right, because Hessian has only positive phi.
Yes, yes. Yeah, so phi cannot be linear. Okay, so right, and then yeah, this is what we saw before. Now, in discrete time, what's the difference? In discrete time, if we look at this natural gradient flow in the primal space, if you want to discretize this, a basic way would be really just to do what we did before with the forward method, right? So here we approximate this vector field just by the value at pk. Right? This, let's say this is assuming that you don't go out of your domain. So this is fine, but this requires this Hessian computation, right? Which may be expensive. So instead, what mirror descent does is that let's discretize in the dual space. Right? So here there is no Hessian. So when we discretize, we don't need to use any Hessian, but instead we need to implement that using what's called mirror descent. What's called Bregman divergence. So mirror descent is So this update is the forward method for discretizing mirror flow. And it turns out that this update we can implement by minimizing this objective function. Yes.
Yeah, sorry. What you said is not super clear to me. Why is the primal Hessian-Riemannian update more costly than the mirror descent update?
In the sense that it requires this Hessian.
And the other thing requires solving a convex problem.
True. Sometimes in some natural examples, like on a simplex, we know
Sure,
it's
but sometimes, but in the same cases, the Hessian is also trivial to calculate.
True. Yes.
So I'm not sure I see
So
why
it is
one.
the inverse of the Hessian, no?
It is
The inverse. It is the inverse. First of all, it is the inverse of the Hessian applied to a vector, so it is matrix vector. The second, it is not the inverse of the Hessian of the objective. It is the inverse of an offline available metric, which is explicit. I mean, in the case of the simplex, this matrix is just diagonal axis. So I'm not sure.
Yeah, that's for the question. Okay, so maybe let me revise my point and say that in general, for this kind of Hessian metric calculation, there is this phenomenon where if you do things in the dual space, you can go down one derivative lower. So that's illustrated here, going from Hessian to gradient. So this also happens when you look at accelerated methods, when you look at how to generate accelerated methods using Hessian geometry. If you discompose in the dual space, you also don't need to use Hessian. And it's also when you look at some more elaborate properties like curvature and so on. Typically, in the dual space, you get lower computational overhead. In the sense that you don't need to go as high derivative.
But it's not the higher derivative of the objective. We agree, right?
Yeah, it's not of the objective. Yes.
This would be just multiplication by this diagonal matrix.
In this case, yes. Okay. Yes. In the yes.
Okay.
Yeah, thanks for the question. Okay, so mirror descent, and as is usual in optimization, when you do a forward method, this is a descent method for small enough step size. Descent method meaning that this discretization decreases your objective function f if you choose the step size to be small enough, and assuming your objective function, this will be capital F, is smooth relative to your convex regularizer phi. And if you have strong convexity, you can improve that to exponential convergence rate. And on the other hand, if you do the backward method, right, so the difference is that now you put pk plus 1 here. This you can implement by solving this optimization problem, where now you are minimizing not the linear approximation, but the objective function itself, still plus the same regularizer. And this is different because now this backward method is always a descent method for any step size. It doesn't require smoothness, it doesn't require any other assumption, but you need to be able to solve this implicit update, right? And you can show exponential rates under strong convexity, but still without smoothness. So this is one difference between the forward and backward update. And this condition, by the way, is not just for analysis technique, but this is actually true. This is actually not true when step size is large enough, even for the quadratic example. But if you run quadratic gradient descent for minimizing quadratic function, if you choose your step size large enough, then you can actually increase. Right? So, okay. So in optimization, we have a relatively milder picture where in continuous time, everything converges, everything contracts, right? Because we are minimizing something. And in discrete time, we have to be a bit more careful. The forward method introduces some error, but under smoothness, we can show that the error can be folded into the contraction, so we still converge. The backward method doesn't require smoothness at all. We always converge. Okay, so this is for optimization. Now let's see what happens for the min-max case, still for mirror descent. So for now let's go back to this basic problem min-max P transpose AQ. The algorithm we study is this alternating mirror descent, where P now uses mirror descent to minimize the objective function. This is also the linear approximation, plus this Bregman divergence. But Q uses the new value pk plus 1. That's like the forward backward. So alternating means they do one step, they make the moves one at a time. And mirror descent means they use these different regularizers on their spaces. So if we follow the same technique as before, let's write down the optimality condition in terms of P and Q. Sorry, this should be psi, but if you want, let's assume that phi equal to psi for now. Right. So in the dual space, they become this update. And as before, sorry, yes.
Can we go? Somehow I want to see an analogy. Alternating gradient descent is a descent where alternating gradient descent ascent would be an algorithm where I will apply first an improvement to pk plus 1, and then in the second one I will have, I have pk plus 1. Okay, yeah, sorry. It was a little bit fast for me. Yeah, it's fine.
Please feel free to ask questions. Okay, so we write down the optimality condition in terms of these new variables, and let's just define the new variables. So let me define the dual functions. Let me call f to be the dual function of phi is the regularizer for p, and g to be the dual function of the regularizer for g, the second pair. Then let me call the dual variables x and y corresponding to p and q, and you can infer this and say that p is the gradient of phi star of x, and phi star is f. So in terms of the dual variable, you get this. And then the algorithm that we are studying is really this algorithm, where the xy variable, we are taking this, looks like a gradient update for g, and then for y, it looks like a gradient update for this function f, still with alternating, right? And here, our observation is that this is an alternating discretization of what's called, or what we call a skew gradient flow. What does that mean? Well, if we take the step size to 0, if we take the limit of the step size to 0, we recover the following continuous time ODE, where x flows following this negative gradient and y flows following this positive gradient. And the key property of this dynamics is that it conserves the energy function. And here we define energy to be this function f of x plus g of y. And here, this is easy to see because you can check that the time derivative of this energy function under this flow is equal to 0. And this is by chain rule. And then here, if you plug in x dot to be this value and y dot to be this value, you get 0. And here is also where you see that it's important to have 1 minus here and 1 plus here, right? Okay, so this is in terms of the x and y variable. Let me call z to be the global variable x, y. Then really we can say, we can define it more generally at least, that given any function h, which is differentiable, let me pick a matrix J, which is skew symmetric. And then let me define skew gradient flow as this ODE, where the velocity is the gradient multiplied by the skew symmetric matrix. Okay. And this recovers the alternating mirror descent case when this h function is this f of x plus g of y, and this matrix J is this skew symmetric matrix. And here's a pictorial description when we will later assume that the function h is convex. So the contour sets look like a convex set, right? And what this dynamics does is that the velocity at each time is always orthogonal to the contour line like before. And therefore, this skew gradient flow conserves the energy function. The ODE, your solution always stays in the orbit of constant energy in continuous time. So this is for a general skew symmetric matrix. Later, if I may speak a little bit about, there's a very special case when J is what's called a symplectic matrix, then this ODE becomes what's called a Hamiltonian flow. So it has a lot more nicer properties like symplectic form and so on. But even at this level, let's see how far we can push this just by assuming this skew gradient flow. Okay. So roughly here's the what we will see at the high level. In continuous time, the skew data flow conserves energy. In discrete time, we have different behavior similar to what we have seen before. Especially, in particular, let's assume that this function h is convex. Because this is true for us because h is a dual function of the regularizer. The forward method always increases energy because you really go out from your current point. The backward method decreases energy, so it converges. And the alternating method is still a bit more complicated. In general, we expect it to preserve energy better. And there are some bounds we can say about that I will get to.
So if I mean, if the Jacobian was symplectic, then the alternating method is actually a symplectic operator, right?
Yes.
So
yes.
we know that approximately it will preserve.
Yes.
It will follow the continuous dynamic. My question now is there somehow a way to measure if I am far from a symplectic behavior, like what is the distance of J and J transpose? If I am far from the symplectic, then I can understand what is happening in the alternating method.
Yeah, a very good question. I don't know. Yeah, no, we haven't thought about that. That's very interesting. Yeah. Okay, so let me show briefly what happens in each case, but it's really the same as before. The forward method, right? So we really apply the backward field at the previous point. And for min-max game, this corresponds to this update. And in the primal variables, this corresponds to simultaneous mirror descent, where the P and Q players play simultaneously. Right? In this case, when the energy function is convex, then it always increases your function value in each iteration. And this is true for any step size, even when your step size is very, very, very large. And really, this is because you can just write down the difference of the energy function. And what comes out is the Bregman divergence of your energy function at successive points. And because H is convex, it's always non-negative. Yeah. And moreover, if you assume strong convexity, then you can say that this is always at least something. So you can improve this to get exponential convergence rate. But turns out that we can also show a lower bound. So if you assume that H is convex and smooth, then the energy function has to increase at most exponentially fast. So your behavior is actually constrained. It really grows exponentially fast and up to some rate. And for min-max game, as before, this translates to the statement that simultaneous mirror descent has the square root T regret bound. Okay, now for the backward method, this is the implicit update. So you have to be able to solve this. For min-max game, the update is also implicit. And for in the primal variables, this corresponds to running simultaneous proximal mirror descent. So you need to be able to solve this equation. But now we get the opposite behavior, that in each iteration, your function value is decreasing because in each iteration, you lose this Bregman divergence. And then if you assume strong convexity, you can improve this to say that your energy function goes to 0 exponentially fast. And there is also a corresponding upper bound. And then this corresponds to the statement that the simultaneous version of the proximal mirror descent has regret of 1 bounded in time. Right? And this is very related to what Jorgos talked about, clairvoyant multiplicative weight update. And also there are some, the optimistic and extra gradient version of mirror descent in some sense tries to approximate this behavior. Okay, now for the alternating method. So let's run, so X runs the forward method using YK, and Y runs the backward method using the new value of X, right? So the update now alternates. And here it's more, all right, and this corresponds to the alternating mirror descent as we saw before. Now, the situation is a bit unclear, but here's what we can say. So let's define what we call the modified energy, where h is the previous function that you start with, f of x plus g of y. And then let's subtract this product, gradient of f times a times gradient of g. In the quadratic setting, when h is quadratic, when f and g are quadratic, this recovers the previous definition of modified energy in the previous paper by Yorkios et al. Here, for mere descent, what we can say is the following. In each step of the alternating method, this modified energy changes by some quantity, which turns out to be equal to what we call the Bregman commutator, which is the difference between the Bregman divergence one way versus the other way. And here's a figure. So this is the definition of the Bregman divergence. And if you unroll the definition of Bregman divergence, excuse me, this is the definition of Bregman commutator. And then if you unroll the definition of Bregman divergence, you get this expression. And this expression by definition measures the non-commutativity of Bregman divergence, right? So if this is your energy function, this is Bregman divergence one way from z to z prime, and you want to compare that against this other way from z prime to z. Let's see the difference of this one minus this one. By definition, it's anti-symmetric, and moreover, it is zero even only if your function is quadratic, right? Because zero means your Bregman divergence is symmetric, and that happens only when h is quadratic. And moreover, usually Bregman divergence is bounded like a quadratic function between z and z prime. Here, Bregman commutator is the difference between two second order terms. So we can bound it by a third order expression under third order smoothness. So okay, so if we look at this, yes, please.
Sorry, there is something that I don't understand with this last condition. If I remember correctly, you assumed that h is a stick, meaning that its gradient explodes at the boundary, right?
That was for phi. Phi is the regularizer.
What is h then?
H is f plus g. So I'm in a dual space, f plus g, where f is phi star and g is.
Oh, I'm sorry, I was lost. Thank you.
No,
Thank you.
So the conditions here, this holds, for example, for the dual function of entropy. If phi entropy, then f and g are the log sum x function, then h is at the sum of two log sum x, and then this is satisfied. Yes.
Out of curiosity, I think that you have a plot there where you're trying to explain also the equality geometrically. Is there a way that I should interpret it? No. I mean, in the slide that you were, I speak about the Bregman commutator.
Yeah.
How I should interpret it besides the difference? You say that the difference is equal with what? Is something geometrical?
This way, the difference is equal to the difference between the commutator is equal to the difference between the modified energy for this alternating method.
Okay. No, I was trying to understand if there is something geometrical from the second equation that you described in the next slide.
Oh, this one.
Yeah.
From here to here, you plug in the definition of the Bregman divergence.
Okay, but there is no way to see geometrically the second equation.
I see. There is, it's not this picture. Comes out like that's the proof of this one that you can write it as some like integral interpolation and so on. Maybe I should also say that this kind of expression also comes up a lot in the sampling literature, for example. If you study Hamiltonian Monte Carlo or Metropolis of just quantum dynamics, this kind of function comes out in bounding the acceptance probability error. And but I don't know if there is a really good geometric interpretation of this. Yes. Okay, so in the quadratic setting, this recovers the result by Yorkios et al. Because in the quadratic setting, this is zero, so we know it's exactly conserved. In the non-quadratic setting, we cannot throw this away, but we can bound it. So. Right, so this is for the quadratic case that we saw before. Now, for the general case, let's assume that our h, which is f plus g in the dual space, is Lipschitz, so the gradient is bounded. Third order smooth, and this is with respect to any node. Then along the alternating method, the difference between the modified energy scales as some constant times steps as cube times k, like the iteration. And really, this is because we can write down the difference in terms of this sum of commutator, and each one is bounded by this step as cube. And the Lipschitzness is just to ensure that this update doesn't blow up. So this holds, for example, if we in the multiplicative weight update case, when h is the dual function of entropy, so this log sum x, and then you can compute all these things explicitly. Okay, so this is not very satisfactory because there is still this linear dependence on iteration. But let's see what we can say with this in terms of regret. But here's a quick summary of what we have seen so far. That in contrast to the optimization setting, the game setting is more interesting, perhaps, because in continuous time we have this perfect cycle. In discrete time, we can either diverge, right, increases energy, increases volume, or we can converge, decreases energy and volume, but this is implicit. Or there is this, there is like anything in between. In particular, one thing is when you alternate between them. Here, we still cannot quite answer this question, but the volume conservation is true. But yeah, but here we are pointing out that there are other classes of interesting dynamics that we can study. So, for example, our bound for the increase in energy function translates to the following statement about regret. That let me go through the definition because hopefully, so what happens here is that in the alternating update case, there are really two half steps here. P makes a move and then Q makes a move. So the regret for the P player, for example, should take into account this payoff and then this payoff, right? So that's what happens here, and then minus a reference point. Similarly, for the second player, we just do a different slide of accounting. So you take this update and this update, and then when you sum them up, most of these terms cancel with these terms. So you get this reference minus this reference plus something constant, right? So if you look at this regret definition, and then you maximize over the reference points, what you get is the following that we saw in the beginning of the talk, that the average regret, if you divide by t, is equal to the duality gap of your average iterates plus something that decays as order 1 over t. So you really need to care only about this term only. Right? And if we plug in our bound, sorry, not our bound, what you can show is that under this definition of regret, if both players follow the alternating mirror descent algorithm, then the regret you can actually write as the following. There is a constant term that doesn't depend on t except for this one. And then there is a second term that is the difference of your modified energy. So this is the the new definition of modified energy, right? So all the summation and so on telescope and you get this difference. Now we can say something, right? Because h is convex, this is negative, we can throw this away, right? This is a constant, let's assume it's a constant, and then this we can bound. Okay. So if we plug in the bound from before, so we get this regret bound, so we get 1 over step size plus step size squared times t, and then if you plug in, if you choose your step size to scale as t to the minus 1/3, this gives you regret bound of t to the 1/3. Right? So this is slightly better than the square root t bound from the forward method, but still really far from the continuous or the backward method, which has constant regret. Okay, so can I take 5 more minutes to go through some figures? Okay, so essentially this is what we can say concretely, but let me say briefly about like what we hope to do. This is part of the something that's still in progress. If you look at what happens empirically, for example, so this is the case when f and g are the log hyperbolic cosine, which is basically what happens when you do the multiplicative weight update in 2 dimensions, like 1 and 1 dimension. when the step size is small, these are the trajectories. The actual energy oscillates, but the modified energy is not quite constant, but it just wiggles a little bit, right? If you increase the step size, your iterates become a bit different. Your energy oscillates a lot. Your modified energy still stays bounded. And here we really care only about small step size, but for this example, at least, you can't really push it. Okay, sorry, I'll show the other example in the end. But from these and other examples, what we really want to say is that we want to be able to say that the energy or the modified energy should really stay conserved for exponentially long time, or hopefully for all time. And one reason we can hope that is the following, as what was pointed out before, that in a special case, when your matrix J is what's called a symplectic matrix, by definition, J is symplectic if it satisfies this equation, where this omega is the standard symplectic matrix. So for the min-max game, this happens when your payoff matrix is a square root of the identity. Okay. So in this case, the skew gradient flow really has what's called a Hamiltonian flow structure. So I won't go into too much detail about that, what that means, but one important property is that this not only conserves your energy value, but it conserves what's called the symplectic structure, which is this sum structure on the space. And that's very good because if we run some discrete sum algorithms, for example, what's called a symplectic integrator, then we can expect that we should have long-term energy conservation. And that's what we want to exploit. And moreover, once you have Hamiltonian structure, then you have a lot of nice properties. Like there is the whole world of symmetry and conservation that you can exploit, like using Nether's theorem and so on. Okay, but for us, the symplectic structure is what's nice. So for example, let's look at this basic case when the payoff is identity. So very basic game. Then we really have this Hamiltonian flow. And then the alternating method really becomes what's called the symplectic Euler method from numerical analysis. And then classically, there is this theorem that under some nice conditions that I don't specify here, that has to do with the analyticity of this and then the bounds on the gradients and then a few other things. We can say that for step size which is small enough, your energy function from time 0 to time t grows like this. You still have some linear growth, but now your dependence on step size is exponentially small. If your step size is very, very small, this e to the minus constant of the step size really goes down to 0, right? So for example, there is like this beautiful textbook by Hiro et al. So if we have something like this, then let's just see what we can do. We can plug this into the regret bound and we get the following expression. Now, then we can choose the step size to be logarithmic, right, in t, and then this will give us some polylog t bound for the regret. But of course, the key difficulty is that these nice conditions have to be really checked. So what we are doing right now is for some basic settings, we can say some results, but we are trying to see how far we can push this and for what kind of functions can we say this is true. And also this is the special case when A is identity. So in general, in general, the dimensions don't even have to be the same. Okay, so this is what happens in the theory side. And then on the empirical side, this is what we saw before for the log hyperbolic cosine with small step size. If you increase the step size, they become more interesting, the trajectory and the energy function. If your step size is very, very, very large, then the trajectories become these two separate things. But now we can also try to combine them. So quadratic plus hyperbolic plus log hyperbolic cosine. So for small step size, they still look okay. For larger step size, you start seeing instability. But again, like we care about the small step size regime. And yeah, you can play around with this cubic function and so on. Okay, so to recap, so in this talk, we explored some topics related to the difference between continuous time dynamics and discrete time algorithms, right? And the different discretization methods and how they have different behavior, especially the distinction between optimization dynamics and games dynamics. Because in optimization, everything converges so that even if you have small deviation, you can still correct them. In in games, in continuous time, you cycle. So like a small perturbation can send you off in different directions. And we also saw how to handle constraints with mirror descent. And that's nice because we can map to this dual space using Hessian metric and so on. So these are the figures from optimization that we saw before. And these are the behavior from min-max games. And in general, I think there are many interesting questions here. So one that we are trying to finish now is proof for what class of functions we can really say this long-term conservation. But then everything so far really is only about two-player min-max game bilinear payoff. We can look at multiplayer games when your update can become either asynchronous, or you may have some SGD style updates, or you have cyclic updates and so on, right? And we can understand what's the different behavior you can get there. And a lot of this really requires a better way to translate results from continuous time to discrete time, right? So far, we have a lot of beautiful results from continuous time and some parallel results in this discrete time, but there is still not an automated way to go from continuous to discrete. So that would be very nice. And the other thing is that now there seems to be this new, there are a lot of these new structures that come up in dynamics and algorithms, all these recurrence theorem. And from this talk, I want to highlight Hamiltonian structure. So this has come up in many places. For games, Jorges a few years ago had this beautiful paper that says that if you have a general network zero-sum games, and if you run for the regularized leader, then they have a Hamiltonian structure. In optimization, the Hamiltonian and the Lagrangian structure also came up in accelerated methods in continuous time because we have second order ODE. And there it's important that we use the Bregman version. And also for sampling, it comes up in Hamiltonian, Monte Carlo, and so on. So I think the field is ripe for more innovation. And so yeah, and I think this workshop is a perfect place to do that. So thanks everyone, and I'm really happy to answer any questions.
Thank you for the great talk and the great slides. So my question is, do you think there exists a perturbed energy function that will be remain constant? And do you think this perturbed energy function has a simple form? Like, because even if it exists, maybe, you know, it's like, I don't know, arbitrarily complicated to compute, but do you think it will have a kind of simple form, just like in the bilinear case?
Yeah, good question. The answer is I'm not sure. So right now, let me see what's the definition of the modified energy. This one. So this modified energy is, in general, there is this theory of modified Hamiltonian, and this is the first order correction of the energy function. So in general, you can expand with more orders of step size. And there are these classical numerical analysis techniques saying that, again, under some nice conditions, you can expect that this truncated modified Hamiltonian really preserves your energy very well. The difficult part is making the bounds and the constants explicit. And yeah, so right now what we are doing is partly trying to understand what we can say without hitting all these difficult classical results. Because apparently, if you let the energy function to be completely arbitrary, then there are other examples that say that you can escape and diverge. But here we are in a very nice case actually, because this H is convex, for example, it's a dual function of something. So we can, yeah, we're hoping to explore more properties. But yeah, but just to answer your question, I don't know if feels like there should be an actual constant quantity, but I don't know if we can cut it down.
Thank you for the very interesting talk. I would like to ask now a question. So, okay, symplectic integration and the final part is interesting, but at the end of the day, you need, for example, to be Hamiltonian in the structure, to have in the correct correspondences in X and Y in order to make it Hamiltonian. What I get as a message that I found that is interesting is that, look, the forward method is that, the implicit is the beautiful but impossible. But look, especially for the game, because I have the min-max situation, I can apply something in the middle and get something better, because that was the comment that I got better regret.
Yep.
I'm not sure if it can be stated as a question, but is there something between? I mean, I can see that, I mean, is the, between alternating and implicit, is something in the middle that could be dreamfully better?
Interesting. Yeah, in general, there can be a lot of things that this whole
In other words, and I should expect something like a better regret, like T to 1/4.
Good question. I don't know if there's a good way to combine alternating and proximal. But if you want to approximate proximal, you can optimistic and so on. So I don't know the answer.
I'm sorry, a follow-up question on both of you. Why wouldn't mirror approach satisfy what you want, or optimistic mirror descent? That would be perfectly, that would have perfectly
Between of those two,
like properties. It is a second order
like
approximation.
an alternating.
Not even alternating. Just
Yeah.
optimistic mirror descent. This is an implementable second order approximation. I mean, why?
Yeah. Yeah, no, very good point. Yeah, I think I agree that if the goal is to minimize your energy as fast as possible, then you want to reach this and you want to run optimistic or something. Yeah, I think here part of our goal was also to explore the different dynamics and understand the different behaviors. And yeah, so the goal wasn't necessarily to get the fastest converging algorithm, but just what we can prove here.
Yeah, now I have a follow-up question. So if convergence, okay, so I agree with Panagiotis. If convergence is my issue, then I will do optimistic, I will do mirror prox. Is something else that energy says to me that it game theoretic, that it is interesting? That, in other words, let's not converge, let's keep energy, but what is the meaning of that, to be happy with that from game theoretic meaning to preserve?
Yeah, I mean, I don't know, maybe that convergence is like good solution concept or something, right? That we just saw. Yeah, I think, yeah, well, hopefully this opens more discussion for like, whether this is something meaningful that we can, try to use and so on.
If I'm going to jump here and maybe, like combining some of the lessons from both of the last talks. Okay, so Christos said, okay, think of games as putting in an input measure, right? But now you have some energy that gets invariant. Then you have some information, right? That your measure over any, the total measure over any level set stays invariant, right? So, for example, this information can constrain what are the possible limit behaviors we see in your system.
But then I'm confused because Christos said that we like the sinks, and the sinks here in energy is clear that it is the center points in the energy.
No, but it depends on the dynamic, right? If the dynamic is something like going backwards in time, like a proximal method or clairvoyant, then it has a point sink, right? But dynamics like alternating, they just naturally cycle.
Okay, I see.
Yeah, so I think maybe an open-ended kind of question is, okay, so in optimization, things are like, as you said, rather straightforward. Here, in some sense, moving the most vanilla class of games, let's say 2-player zero-sum game, you say like, okay, take very natural algorithms from any algorithm textbook. They have totally different analysis with totally different proofs. How should I think about this? Is this good news? Is it bad news? Yeah.
Yeah, thanks for the questions.
Maybe commentary. Like, do you think that it's an opportunity, or do you think it's the problem?
Of this phenomenon?
Yes.
I think, well, for my case, it's a big opportunity because, yeah, as you said, this is even for the case of 2-player bilinear zero-sum game. Right? Once you move to non-bilinear, like a lot of this structure goes away. Once you move to beyond 2 players, a lot of this thing goes away. So there might be a way to embed general dream into something that looks like this, that something like this works. But yeah, I think my sense is that this illustrates something that's sort of like a small hint of what else we can say. So hopefully it's an opportunity.
Great. Any more questions? Okay. Let's thank Andre again and all of the speakers. Thank you.
It's like